I'm looking for the person I usually get to do this, but they're not there. And let me find out about the recording also. This is supposed to record automatically.
Do you want me to send you the YouTube link after class?
Yeah, that'd be great. Let me see if this does this. It's supposed to record this, it says.
It says it's recording now, Dr. Baginski.
Thank you very much. Unfortunately, when I'm sharing the screen, I cannot see some things. Thank you. All right, is everybody with me? Can you hear me okay and see a yellow screen that's being cast? Can you all see that, everybody?
Yes, we can see it.
Okay, got to make sure you can. All right, what we're doing is transients today. Now, let me explain something. In the book you purchased, on page 75, he goes through transients. Now, he does it from the perspective of, I'm sorry?
Oh, sorry, I didn't know it was
Thank you very much. I'm so sorry. Give me once. I mean, can you see this? Can you see the book or not? You can. Gunn, what were you saying?
sorry, I didn't know my mic was on. Sorry, sir.
I think I just muted. All right, what I'm trying to tell you is this is in your book. And he does it and he uses Laplace transforms. Now, transient problems in general, let me give you what it boils down to. It's when you have a circuit that either has current voltage in it or doesn't. And then the state is changed. So immediately it goes from, say, no voltage to a connection where there is voltage. It's called a transient. It's a very common thing. You've had this in physics. You've had it in mathematics, in your math courses, and I'm sure you've had it in your engineering courses. What I'm going to do is skip over the Laplace transform approach and tell you two things that are important. The first thing is we don't do second order differential equations, which means your equations are just going to have exponential decay plus a constant for either voltage or current. Does everybody hear me on that? This is essential. They're going to be trivial. The second thing is, when we do this, we're only going to consider capacitors and resistors by themselves or inductors and resistors by themselves with sources. Okay? Now, having said that, the best way for me to do this, and I think everybody will appreciate the simplicity of this if I do it this way, and I hope they do, is I'm going to start with a transient problem. I'm going to take the book out and I'm going to just show you right here. You've all had capacitors. You've all had resistors. And I assume you can see this, and I know it's a bit out of focus. But can you all see this right here? Now, here we have a current IC going through the capacitor. The capacitor has a value C, and a current to the resistor. But the current coming into it, I'm going to have 0. So no currents coming into this. Do you all follow me on this? Now what I'm going to say is this. I'm going to say current going in is 0. Current leaving is IC plus IR, and that's equal to 0. Does everybody agree with me there? Right? Whatever goes in comes out. Correct, class?
The paper up a little bit.
Yeah, thumbs up. Just give me some evidence that you're there. I mean, I'm trying to make sure I communicate to you directly, and you can give me feedback. Now, when we have a capacitor, I'm going to do this again, and it has a voltage plus to minus V on the capacitor. You can put it V as a function of T if you'd like. It develops a current I that's a function of T, and the relationship is C times the derivative of that voltage with respect to T, notice the actual polarity, plus to minus, is equal to the current I of T entering the positive terminal. Can everybody follow me on this? You've had this in physics, but you probably haven't used it all that much. With me? All right, how many remember seeing something to this effect somewhere back in the day? In physics and math and, okay, good. Oh, Jessica, there you are. I'll make you a co-host too, that way I think more people, the better they're recording. Now, what I'm going to do next is simply replace IC with its voltage equation. So IC is equal to, right here, C dV dt. And what's the current through the resistor? First, let me step back. Does everybody agree that the voltage across the capacitor is the voltage across the resistor because they are in parallel? With me? Agreed? All right. I'm hoping to get just a bit more agreement, so I know you're there. I'm trying to do this in a way that's not going to go too fast. And the more information I get from you, the better. You all with me on this, guys? All right. That means the current through the resistor is just V of T divided by R, and the sum is 0, right? Here I'm going to simplify things. I'm going to forget the function of T that's implied. And I'm going to go ahead and take this equation and divide by C. Now, if you divide everything by C, you get an RC here. Do you agree with me? And after that, I'm going to go ahead and leave that alone and take this to the other side. So I have dV dt is equal to minus 1 over RC times V. Now I have suppressed the T because it's unnecessary. We know it's going to be a function of time. Now I'm going to do it this way. And this is not with a Laplace transform. This is doing it the way your calculus teacher told you to do it at first. I'm going to go ahead, first of all, and divide by V, and then multiply by dt. So I get dV over V is equal to minus dt over RC. You see, I've divided both sides by V, and then I multiply both sides by dt. How many see this? It's very trivial what I'm going to show you. I just have to make sure you're with me on this. Okay? Now, what I'm going to do is go ahead and integrate both sides of this. Now remember, these are indefinite integrals. So the integral of 1 over V dV, or 1 over x dx, is a natural log. Natural log of V, correct? Plus a constant, all right? I didn't add the constant here, but you all agree there will be a constant that enters in because there are no limits. And that's equal to, right here, it's going to be, well, the integral of dt is t, so it's going to be minus t over RC. Now, it's not important you follow the steps of this. I'm doing this for completeness only. In electrical and computer engineering, I would do it with Laplace transforms, and I'd have a more generalized form of the solution. Are you with me, class? Now, after I have that, I want to solve for V. So I take both sides. Now remember, there's a constant here too. I'm going to put it in here. I'm going to take both sides, literally elevate them to the exponential. So e to the natural log V is just what? V, right? And on this side, it's going to be equal to e to the minus t over RC. And then it's going to be e to the c. Do you agree with that? Take a look, just convince yourself. We're not going to dwell on this because it's really not necessary. Okay, thank you. One thumbs up. And I'm not going fast. And give me feedback if I'm going too fast, too slow. And try not to be too rude, but I appreciate that. Send it in email, chat. It's hard for me to see chat. Now, if C is a constant, e to the c is a constant. Do you agree with that? Yay? I mean, if you got 10, e to the 10 is still a constant. So now we say that v, and here I'll put in a function of t, is equal to e to the minus t over rc times some constant. And that constant for this specific case is the voltage at t equals 0. But in general, it's just generally a constant. Here I'm going to put v naught and box that. That is the solution for this circuit. You all follow me? Now, a simple example that you've seen over and over again. Here, there are no external sources that are getting turned on or turned off. It's simply a statement that whatever the voltage is at t equals 0, which would be V naught, right? Because this right here would just be equal to some constant k e to the minus t over rc. And if at t equals 0, v is V naught. Now, at t equals 0, e to the 0 is 1. And then k would be v. And if the voltage at t equals 0 was V naught, you would have this equation. Do we agree? Everybody? Yay?
Dr. Bajanski,
Mhm.
what's the thing written next to the V between V and an E?
Help me out. Between v and an e,
Yeah, that part right there.
just v
That,
naught. Sub-0 means at t equals 0. That's what I'm trying to say.
okay.
It is just an arbitrary constant. You don't have to put that in there, but it will be the voltage at t equals 0. So if I give you a circuit like this and I said there's a certain voltage at t equals 0, you could tell me what the voltage is for all time. Does everybody agree with that? Now, next, what if I asked for the current through this resistor? How would you get it? If I had the voltage for all time, maybe I'll give you a concrete example just to flesh this out, and then we're going to move on rather quickly. Suppose I gave you this. I have a capacitor, make C equal to 2 farads. That is a whopping big capacitor in the real world, by the way. And then make a resistor here equal to, say, I don't know, 5 ohms, okay? And I'm going to say at t equals 0, and here's how they would do this. They would put what's called a switch, and they would put a battery. And I'm going to say a battery here is going to be 10 volts. Okay? And then I'm going to say the switch closes at t equals 0. So what I'm trying to draw here is that's a battery of 10 volts. Sorry, I got this wrong. Let me redraw that. You can draw this part, but not that part. You have a capacitor. And I'll draw it this way. I'm going to have a battery here of 10 volts. Then what I'm going to do is have a switch that's initially closed and that opens at t equals 0. That's what I wanted to do. And now I'm going to have my capacitor here and let the capacitor be 2 farads. And then I'm going to have a resistor of 5 ohms. And now what I'm going to do is ask you some questions. First, I want to know what the voltage is across these two elements as a function of time for t greater than 0. So I want V of t. This is a typical question. Does everybody understand the problem?
Get your page up a little bit.
Yeah, I got it. And let me just say one other thing. And this is important. This is the symbol for a switch. Now on the wall, you have switches that you flip. The only thing the switch does is either allow conduction or take away the ability to conduct through an electric circuit. So if at t equals 0, it's opened, it assumes it's closed for t less than 0. Correct, class? I'm going to make a couple of comments. Now, for t less than 0, this brings up an interesting point. What does a capacitor look like when nothing's changing? Do you agree when you have that voltage there, for t less than 0, it's been on since t equals minus infinity to just before 0, there is no time varying state of the voltage. Do you all agree with that? All right, how much current flows through the capacitor If there is no time varying voltage, we know what? I in the capacitor is C dV dt, right? You agree with me? I'm going slow here. Y'all with me on this? So if no current flows there, this is one way of looking at it, then therefore it looks like an open circuit even though it has voltage across it. Do you agree with me? And that's exactly what a capacitor looks like when there is no time varying voltage or current. And if that's an open circuit, what does it say the voltage is across that capacitor if that's a short circuit? Or if that's just an open circuit? Isn't it just 10 volts, class? Take a good look. If the capacitor, in fact, is like an open circuit, then the voltage is the voltage across the resistor, which is the voltage across the battery, right, for t less than 0. And you would say that V right there for t less than or equal to 0 would be equal to 10 volts. Y'all agree? Thank you. The more information I get from you, the better I feel about this class in general, and it's easier for me to teach. And I'm not trying to bother you, but it really helps me, and I hope it helps you. So I've got this.
Was the switch open at t's less than 0? Is that what you're saying?
Closed. See how
Closed.
it's a straight line?
Okay, it was opened at t equals 0?
Right. It pops open at t equals 0, and it disconnects the battery from the circuit. That's what I'm trying to do, is emulate a voltage at t equals 0 that's pulled out of the circuit. Okay? Now you can see that when I get the solution to this, this is something that has no source for t greater than 0. So for t greater than 0, then you could say greater than or equal to, and I'm not going to argue about the add 0 thing. I can say that the voltage V of t, based on the equations we just did, would be equal to the voltage at t equals 0, which would be 10, right? We know that's going to be 10 volts at t equals 0. Then it would be e to the minus t over r times c. And r times c for a capacitor would be 10, wouldn't it, for the one I chose? Now the units of r times c, if r is in ohms and c is in farads, is seconds. And that would be the solution of the voltage across this capacitor. Is everybody with me on that? With me? Any questions? And that should make sense because you've seen this a lot. I could write differential equations all the time. I don't need to. I can see I've got a voltage at t equals 0, no other sources for t greater than 0. That's the voltage on the capacitor. Question now.
Is the R the equivalent resistance for, like, say the circuit had
It
multiple?
will be, you're way ahead of me. You're absolutely right. R will be the Thevenin equivalent resistance that's seen by the capacitor for t greater than 0. But you've jumped a couple of steps ahead of me. I'm just trying to make sure everybody here is on this page with me. Y'all with me on this, guys?
Wait, so the equation you wrote down there is the e to the r v naught times e to the negative t RC.
Over RC divided
Over
by,
RC.
do you agree with that? R
So
is
did you write down
5.
105?
No,
Or is
it's
that-
seconds. That's seconds is the units. It's supposed to be 10. I put the units in seconds. I'm sorry if I confused you.
All
I
right,
wasn't
that makes.
trying to be
thank you.
complete. I was just trying to make a point. R in resistance and ohm and C in farads, the product has the unit. Okay, everybody?
You said the overall unit was?
R times C is seconds. Ohms times farads is seconds. And you can go and look this up. There's a lot of different ways to do this. And in chemistry, you know about units, and I'm not going to spend time on that. All right? Accepted. R times C. Now, that's when there is no source. This is very important what I'm about to tell you. In general, when we have a capacitor, write this down. When we have a circuit with a capacitor, and this is going to be an RC circuit. So write this down, RC circuit. And this is a transient circuit. The first step is you find the voltage. Find V for t less than or equal to 0 across the capacitor. The sub C just means across the capacitor. Does everybody follow me on that? That's the first step. You need it. The second thing is, and that's where Evans was way ahead of me, you find the R Thevenin value, the Thevenin equivalent resistance across the capacitor. And I'm going to go through examples. If you remove the capacitor and talked about the Thevenin equivalent resistance that would be across the terminals of the capacitor if it was taken out for t greater than 0, find R Thevenin for t greater than 0. That's the next step. The third step after that is find the voltage across the capacitor as t goes to infinity. Now, this is fairly easy to see, but I'm just going to mention this. All right. When you look at this circuit for t greater than 0, it started with 10 volts, right? This is the prior circuit. Y'all agree with me? What is that voltage going to go to as t goes to infinity? How many know it's 0? All right. It will go to 0. It will decay down to 0. The reason, the primary reason is there's no other source here to energize a circuit and provide energy to keep it a voltage across that capacitor. There is no other voltage or current source. Do y'all follow me? Are you with me at that? I'm going to get to examples where it's not. Go ahead, Joseph.
I was just agreeing with you vocally.
Okay.
I don't have to raise
Good.
my hand.
That's all right. That's good. The more vocal, I think, the better for me. Now, after that, this is important. Remember, the thing we're always going to get when we have an RC circuit with transients, regardless of the amount of resistors or batteries or current sources, if it's a transient circuit, we're looking for the voltage at t equals 0 before the switch does its thing. I should say before the switch transitions. We're only going to do problems with one, maybe two switches that transition at the same time. You find this. The next thing is you find R Thevenin. Now the voltage as t equals infinity is interesting. Remember what I told you. Before t equals 0, nothing is changing with time. The circuit has been in that state since time began, right? So the time rate of change of voltage is 0, and therefore the capacitor has a current of 0, and it looks like an open circuit. Do y'all follow me in that? As t goes to infinity, nothing's changing, all right? It's in a steady state, which means that the capacitor looks like an open circuit at t equal infinity. This voltage may not be 0. The next problem I'm going to do will be a problem where this isn't 0. Once we have this, we get this, and then after that, then the fourth thing, and the order of these doesn't matter. The fourth thing you do is you find the time constant, tau. Now, tau is a time constant. In our case, it's going to be R Thevenin times C. I could have just as easy put this step right next to this step where I said find R Thevenin. I broke it out separately. That was the time constant R times C that you saw here where it was 10 for my sake. Are you with me? Again, we're only concerned about the voltage across the capacitor. Next, once you have that, then you put together an equation for the voltage across the capacitor. And here, don't assume the voltage coefficient for the exponential is the voltage at t equals 0. But then in general, this is the fifth thing. And I could write the differential equations and solve them for this. But the fact of the matter is, it will become painful. If you understood what I did before, up here when I wrote the differential equations, I got it in the page before, you'll understand this. You can do it with Laplace transforms, but this will be the final form of the solution. This you write down. The voltage across the capacitor as a function of time will be, say, some K1. It's not necessarily the voltage at t equals 0 here, times e to the minus t over the time constant, that's R Thevenin C, plus some K2. I'm going to go through some problems so you see this. Here, K2 is actually the voltage as t goes to infinity. Okay, so you might want to write that down. K2, voltage at t equal infinity across cap or on cap. That's what K2 is. K1 you have to determine sometimes, and I'm going to do a problem with this. Now, before I go any further, how many remember vaguely somewhere that you've done problems like this in physics or in mathematics or in your engineering courses? They're called transient problems where you have initial conditions, final conditions, and you solve for the coefficients. Y'all remember those. MEs and aerospace engineers for sure. I'm assuming industrials have done these too, but the problem is I'm not familiar with the processing things that you write equations for. Usually it's difference equations, not differential, I think.
So this is just diff EQ, like you've got a tank of brine at a certain salinity and you're adding a certain amount of saline water to it. What's your final salinity, or how long do you have to fill the tank?
Well, something like that where you've got to figure. Anyway, you guys have been exposed, is what I'm getting at. You're not totally shocked by that differential. I got to tell this story. Now, this is an electrical engineering class I was teaching. This one's good, remember it. And so I wrote down the integral of I of t dt was equal to the charge Q of t. Now, you've seen that from physics. The integral of current dt is charge, right? How many remember that? All right, you saw something like that. All right, now, a student in my class raised his hand. It took me a lot not to laugh. And he said, what's that script S mean? When I heard the word script S for an integral sign, I'm so glad I didn't laugh, but everybody else did. And I tried to explain to him, it's an integral sign, and he looked. And then I thought, we have to talk afterwards. Enough of that story, but that's how crazy sometimes the background gets with students. They don't even know what an integration sign. Now back on topic here. Now I'm going to give you a problem, and I'm going to work it. I'm going to try to give you one out of his book. I've got stuff all selected for you. I'm trying to give you one that's not, give me 1 second. I'm trying not to give you a really complicated one. I'm going to do this problem on page 76 that he has in the book. This is your book. It's on page 76. But I'm going to put actual values for E, that's the voltage source, for R, and for C. Okay, everybody? So if you want to, it's on page 76 of your book. But here, I'm going to use I'm going to use actual voltage for E. I think it somehow retains better with students. Are you all right with that, everyone? I mean, if you want me to use symbols, I will, but I preferred showing you something that's a little closer to what you'll be doing. So I'll rewrite the circuit. You don't have to, but I'm going to do this, and we're all going to do it. And you're going to see, you're going to laugh and say, well, I knew that. I'm going to put a voltage here, again, of 10 volts. All right. I'm going to do this a little different. Yeah, I'm going to have this go like this. And then I'm going to have a resistor. Make R.
Use the paper up a little bit.
Yes, thank you very much. I'm going to make R equal to 2 ohms. Then I'm going to put a capacitor here. I'm going to make the capacitor 5 farad. And I want this voltage. The plus to minus voltage across the capacitor is a function of time. Everybody with me? And this switch is going to close at t equals 0. I'm going to cover some territory here, so please be attentive. Are you with me, everyone? Okay. Now when I have this, That C is 5 farads, that's 2 ohms. I know that the voltage across a capacitor for any transient case will have the form V of t, Vc of t, will be equal to some K1 e to the minus t over tau plus K2. Here I know K2 is going to be really, it equals the voltage, this is equal to V of C at t going to infinity. And I know that tau is equal to R Thevenin times C, right? Now, there's something about that R Thevenin that I didn't state explicitly right here, but R Thevenin is for t greater than 0. So it's after, actually, I should say more generally, it's after the switch's transition. So please watch this. If you don't see it, ask a question. What did I say in the statement before then? First I need the voltage, and I'll do it here. Actually, the order of this is immaterial. I usually start at the voltage across the capacitor for t less than 0. Or is less than or equal to 0. Now, when you look at this, what is the voltage across that capacitor for t less than 0 and a reason for it, anyone?
$10
For t less than 0. Do you see that t equals 0 is where the transition takes place? Do you see the arrow here going like this?
0 volts.
It's 0, right? For t less than 0, that source is not connected to the circuit. So the voltage across the capacitor is 0. Now, how many see that? I got to make a comment too about this. The voltage across the capacitor cannot change instantaneously. For t less than 0, it has a value. For t 0 plus, it doesn't have a value of V naught. It can't. And here's why. It would imply an infinite current, which is impossible. So what you actually have is the voltage across the capacitor is continuous. It will never have a discontinuity. That's very important. If you got the voltage of t less than 0 just before the switch does its thing, it's the voltage just after. Does everybody got that? Now, that's the first thing I need. So I got that. The second thing, I'm going to get this. I'm going to get, what's the voltage? Oh, no, I'm going to get R Thevenin. I like to do it this way. What's R Thevenin? Remember, that's for t greater than 0. So please take a look at this, everybody. Be attentive here. I kid you not when I say people make mistakes left and right, and they look for points and they get 0. So just watch this and listen.
You gotta focus.
Thank you. Okay, for getting R Thevenin, we have to look at the final state of the circuit. That's where this thing's shorted, right? Which closed. Do you all agree with that? Now, in the final state of the circuit, if that's a short circuit and I want R Thevenin, what do I actually do? I remove the capacitor, and that's exactly what I'm going to do. I leave the resistor alone, and that was R equal 2 ohms, right? And then what do I do to that voltage source if I'm calculating a Thevenin equivalent resistance? Class?
Short.
It becomes a short circuit. So what's R Thevenin here? Just look at it.
2 ohms.
Just 2 ohms. Sorry about that ohms. Yeah, it's 2 ohms. Now, right under here, you might as well get the time constant tau, R times C, which would be 10, right? And the units are seconds, but not to worry. Agreed, class? With me?
Yes.
Next, I need, and the order of this is immaterial. I need the voltage across the capacitor as t goes to infinity. Look at the circuit and think about it. At t equals infinity, the switch is closed, right? Do you agree? How much current flows at t equal infinity? Let me redraw that circuit. For t, I have what? I have a voltage here of 10 volts, right? And then I've got a resistor and I've got an open circuit, right? And I want this voltage, Vc of t, because literally the capacitor looks like an open circuit at t equal infinity because there's nothing changing with time. Does everybody see this? Guys? Thumbs up, some way of acknowledging, right? Okay. Not many people acknowledging, that's okay, but I prefer it. Now, how much current flows here at t equal infinity? None, right?
0.
0, zip. What's the voltage drop across that resistor if no current flows?
10 volts.
If no current flows, what's voltage across the resistor? I times R. If I is 0, it's zip, right? There's no voltage drop, which means all the voltage is here. The 10 volts here is 10 volts here. But I'm glad you made the mistake, because I'm going to tell you, so many people will make that mistake over and over and over again. And this is the thing I want to make sure you get a warning. I mean, be warned here. When this is an open circuit, when you take the capacitor out, it means there's nothing time varying there. And if this is an open circuit for the circuit shown, the current is 0, means the voltage across that resistor, regardless of that resistor, is a 0. 10 volts appears here. In this case, it's just going to be 10 volts. Do you agree? Now we assemble the equation that describes the voltage across that capacitor. The VC of t, and this is true for all transients, and I can say this, if the switch closed a second later, then we shift everything we get here by a second. With me? It doesn't matter when the switch does its thing. It's just a reference point. But we're assuming it does its transition at 0, and engineers generally start a transitional state from happening at 0 for simplicity. So V is C, and write this down now. It's K1 e to the minus t. I've got tau already, right? And I've got tau is equal to, what did I make? R is 2, C is 5. So I'm at R is 2, pardon me. And that makes tau 10 right here. So I can say divided by 10 plus K2, right? I just rewrote the equation I put down a second ago. Y'all with me? Good. I mean, if you're still writing fine, I'm not trying to do this in a tricky way. I'm trying to be very clear. And anything I consider a point of confusion, I'll try to really underscore for you. Now, what is K2? What did I say it was?
The voltage at t equals infinity.
Yeah, and
voltage
here's
across the capacitor at t equals infinity.
And this is you always go for the voltage across the capacitor, nothing else when you solve transient equation or transient state RC circuits. Now I got to tell you this, we've got K2, right? So K2 is the voltage at t equal infinity, which is 10, correct, class? That's here, step 3. So I'll put it in as 10. And that's equal to VC of t, right? Now we used one boundary condition, the boundary condition at t equal infinity, right? The other boundary condition was at t equal 0, right? Time 0. Y'all agree with that? And if time is 0, what is e to the 0? Anyone?
1.
1. So that means the voltage at C at t equals 0, so VC for t equals 0 is 0, and that's equal to K1 plus 10, and therefore K1 is minus 10, correct? Got me on that?
Wait, so why is it equal to 0 again?
Well, isn't the voltage at t equals 0 equal to 0? Didn't we establish that right here in step 1? Pardon me. Right here?
Yeah.
Okay, so that goes on this side because this equation is going to be evaluated at t equals 0. And at t equals 0, e to the minus 0 is 1, right? And I'm making that point right here. We're going to have t equals 0, so it's 1. So it's K1 plus 10 is equal to 0. Therefore, K1 is minus 10. Do you agree with me? How many do? How many agree with what I've done there? All right. Got one more, and these are the questions that fumble people on quizzes all the time. Now, this is the equation for voltage. If I go ahead and rewrite it, I say VC of t, therefore, would be equal to minus 10 e to the minus what? T over 10 plus 10, right? That's the voltage across the capacitor. Agreed, class? Now, if I wanted the current through the capacitor, remember that's true for t greater than or equal to 0, period. There's I mean, that's generally true for t greater than 0. Now look, if that's the voltage across this capacitor right here, if I want that current, IC of t, wouldn't that be equal to C times dV dt, right? So I could take a time derivative of the voltage across the capacitor and multiply it by C, and I would get, in fact, the current. Do you all agree with that? That's one method. How many see that? By definition, right? C dV dt is equal to I. If we have an equation for V as a function of time, we could take a derivative, multiply it by C, and get I through the capacitor. Do you all agree? Or thumbs up, right? Another way we could do it, listen, we've got a voltage here, right? You all see this. We got a voltage across the capacitor. I've got 10 here. If I wanted the current here, which would be the current through that capacitor, I could take 10 minus this voltage, which I have here, right? And divide it by 2. How many see that? Right? I could
Say that again.
I could take the voltage here, this would be on the positive side, minus the voltage here, which would be VC, and ground that to help see it, right? Voltage here minus voltage here, that's a voltage difference. If I divide it by 2, I have the current. Correct, class? How many see that? The voltage with respect to ground here is 10, period, amen, and that's for t greater than 0. That switch is closed, right? The voltage here is VC of t, right? With respect to ground. Therefore, this voltage minus this voltage divided by 2 would be the current. So to get the current there, there's several ways. I could take either C dV dt, or I could take 10 minus VC of t over 2, and it would give me the current through that resistor. Do we agree? Either way is fine. How many see this, Bob? And what must that current go to as t equals infinity?
0.
It's got to go to 0, right? For this case. All right. So I got 5 minutes. And the best way I think you can learn this is be exposed to problems. Now, Dr. Gross and Dr. Roppel's book, they do this with Laplace transforms and stuff, but I'm going to level with you. I'm not sure that's the best way to show this because it's so simple. Just write just the simple differential equations and get an integrating factor. In their book themselves, they're a bit light on problems related to transients. He assumes one solves it all for everyone, and I don't believe that. I have taught this course and others many times, and I know one thing that's true. Exposure to a variety of different problems is the key to understanding transients. So I'm going to give you a few, and I've got another Irwin's old book. I got this Irwin book. I've got Hayton Kimmerly. I don't know whether I've got sources from all over. I'm going to try to give you ones that make you think, but don't overwhelm you. Like, I don't know where to begin, Dr. Baginski. Can you give me a hint? I'm going to just give you some that don't tax you too far, but are going to still be something that causes you to think. All right. Now, can you all work with me on this one? All right, here we're going to take 3 milliamps. This is 3 milliamps, or 2 milliamps. And then we're going to have a resistor of 3K. There are many ways to do these, by the way. That's going to be a 3K resistor. Here we're going to have a switch.
Can you set the paper up?
Yeah, and this switch is actually closed at t equals 0. It transitions to open. So it goes from closed to open. Then I'm going to have a capacitor here. And that capacitor has a value of 300 microfarads. Micro is 10 to the minus 6. Then I have 3K. And then I have 12 volts. So I got 2 milliamps, 3K, switch opens at T equals 0. Then I have, this is 12 volts, let me put it here. And 3K there. And I want the voltage across this capacitor. Are you with me? Now, here's where you use your basic circuits analysis techniques to get things. I know the first thing I want is voltage across the capacitor for T less than 0, right? You agree with me? So I know for T less than 0, the capacitor has 0 current. It looks like an open circuit. How many agree with that? For T less than 0, there is nothing changing. And remember, current through a capacitor is C dV dt. So if there is no time variation of the voltage, there is no current through the capacitor. It's 0. Agreed? Looks like an open circuit. So I'm going to replace that with an open circuit. I'm going to go ahead and put in the 2 milliamps. I'm just taking the circuit I've drawn, putting in 2 milliamps, then I'm putting in 3K. Now that switch, this is going to be for T less than 0, is closed, right? Then I have my capacitor here. I'm going to take the capacitor out of the circuit, and I'll just call that VC for T less than 0, right? Then I got a resistor of 3K and a voltage source of 12 volts right there. Everybody with me? I've simply redrawn the circuit, removing the capacitor and removing the switch since it's in a closed state for T equals 0. I want this volt.
So why did you remove the capacitor again?
To help you better see what I'm after. I'm trying to show you what that voltage is across it. It's a short circuit. It's like, an open circuit. It's not there. Are you with me, people? Show a thumbs up, anything that and by the way, we're right now at 1:50 according to my clock. So if you have to go, but I'm going to finish up this problem and then take office hours. Are you with me, everyone? Okay, good. Now, when I do that, how do I get this voltage? This is a very common type of problem on a quiz. How do I get that voltage? Well, what could I do? Let's talk about the options. Do you see I could do a source transform here? That's one option, right? How many see that? But probably these two are in parallel. A source transform here might be a little easier because the two resistances will be in parallel and so will the current sources. Do y'all agree? I'm going to do that. I'll redraw this and I want to make sure you see this. I'm going to do a source transform of voltage in series with resistor to current in parallel with resistor. So on the left, I have 2 milliamps and then I have 3K. There's where I'm looking for the voltage, right? Plus the minus VC, right there for T less than 0. And then I have, now that resistor becomes in parallel here. This is the source transform, that's 3K. And then I have what? A current source. What's the current source? If that's 12 volts and 3K, the current source would be what? Four milliamps. Do you agree? It would be 12 divided by 3K or 4 milliamps, right? How many see this? This will help you, believe me. Now, if that's the case, remember, I'm after this voltage. What's my next step? You can do this a bunch of different ways. There is no one best way, but what would you do? Anybody see something that can be combined?
Current sources and the resistors?
Yeah, sure. The two current sources are both going into this upper node. So, and they're both what? Going positive into it. So it'd be 4 and 2 would be 6 milliamps, right? Agreed? What about these two resistors? They are in
Parallel.
Parallel. So 3K and 3K would be 3K over 2 or just 3/2 of a K, right? And here's my voltage, right? That's what I'm after, that VC right here. Correct, class? For t less than 0. All right, what is that? Well, isn't that just 6 milliamps times 3 over 2K? Right? And isn't that 9 volts, people? I want you to take a look and convince yourself. If I'm going too fast, I don't think I'm going too fast, but I feel like I'm talking to people watching Monday Night Football or something. Everybody's on, but they're not. Are you with me?
Yes.
Okay.
Yeah.
Now I've got that voltage. Let's go back to the original circuit. So I've got my VC for t less than 0, and I'm going to put it up here. And that's 9 volts. All right. Now, guys, look at this with me. I'll give you a second to get oriented. I know we've been going over 50 minutes. Usually I tell people to take a break. So if you got coffee or tea or water or whatever, or something to eat, now's your time. Then my next thing I need is what? The voltage across that capacitor for what? T goes to infinity. Do you agree, class?
Yeah.
All right, what is it? Now, can you all see this circuit here? That switch flips open, right? That disconnects everything on that side, doesn't it?
Yeah.
Once that switch flips open, everything on the left, and that's the reason I'm covering it, is out of the circuit. It has no way of conducting. Now, what does this look like as t goes to infinity, class?
0.
It looks like an open circuit, doesn't it?
The current goes to 0. So
Yeah,
there's
yeah.
a capacitor.
I think you were saying the right thing, and just I goes to 0, t equal infinity, right?
Like 0.
And therefore the voltage drop across a 3K is 0, correct?
Mhm.
And therefore 12 volts is the voltage across that capacitor. How many see that?
Can you review that one more time, please?
Yeah. Do you follow me on just isolating this portion of the circuit?
You need to slide
Yes.
your page up a little bit.
All right. Do you all agree that this is the circuit for t greater than 0 going to infinity, class? First, you got to agree with
Yes.
me. All right. Now, if we want the voltage on the capacitor as t equals infinity, what does the capacitor look like at t equal infinity? Open circuit, right? No current can flow. C dV dt. Nothing is changing with time at infinity. So therefore the current is 0, or it's an open circuit. If no current can flow, it's an open circuit, isn't it?
Yeah.
If that's an open circuit, what voltage will be here? Well, you got to ask yourself how much current can flow. 0. If no current can flow, that resistor has no drop, right? Gabriella, are you the one that asked this?
Yes.
Okay, I mean, I appreciate you muting yourself and stuff, but this is an office. I'm trying to get the point across to everybody. And your
Yeah,
question.
there was a train going by, sorry.
that would hurt. All right. So now, if that's an open circuit, I didn't draw it for the sake of time, but if that's an open circuit, then 12 volts is the voltage at t greater than 0. I mean, t goes to infinity across the capacitor. Do you agree with that?
Yes.
Now, how many do? I'm getting a spattering of thumbs and a lot of I don't care.
So there'd be basically you could draw a ground right next to the capacitor.
Yeah,
and
and it's not essential, but yeah, you could, right? Sure. All right, so it's 12 volts. Now I've got 2 voltages, and I'm going to put them here for everybody's sake. I've got VC for t less than 0 is equal to 9 volts. Now I got VC for t goes to infinity is equal to 12 volts, right? With me?
Yeah.
Let's go back to the circuit. Now stay with me, guys. I'm sorry that's getting a little sloppy. For t greater than 0, do you agree that part of the circuit is gone? Everybody? Because the switch is open, right? It disconnects everything. Agreed?
Yeah.
Okay. 1, 2, 2 and a head bob, 3. Okay. All right. If that's the case, now listen, I need the R Thevenin across this capacitor when I rip it out, right?
Yeah.
So when you take that capacitor out, what's R Thevenin across there?
3K.
Ohms.
Right, 3K ohms actually. That battery is shorted, right? Right?
Yeah.
Okay, that's good. So that means R Thevenin is equal to 3K. Let's go back here. We saw that C was 300 microfarad. I'm going to go back down and write this. So 300 microfarad is C equals 300 times 10 to the minus 6 farad. That's really what? 30 times 10 to the minus 5th, 3 times 10 to the minus 4th, or 3 times 10 to the minus 4th farads. And it's times 3K, right? So my time constant would be 3 times 10 to the minus 4th times 3 times 10 to the 3rd, right? Or it's going to be 9 times 10 to the minus 1, or 0.9 seconds, right? Just multiply R times C. I made this more complicated than need be. If you take 300 microfarads and multiply it by 3,000 ohms or 3K ohms, it boils down to 0.9. You agree with me, everyone?
Yeah.
Yeah.
All right, now here's the golden step. Finally, after all that, I assemble the equation for voltage, and I say that VC of t, right here, is equal to K1, just leave it as K1 now, e to the minus t, and you can just leave over tau if you've got it up here, because I know tau is 0.9, plus K2. What is K2 always, class?
9 volts.
What is it in general? It's the voltage across the capacitor as t goes to what?
Infinity.
Infinity. Isn't that 12?
Yeah, I thought it was as t is below 0.
T less than 0, it would be 9, right? But for t goes to infinity, it would be t positive infinity would be what? Isn't that 12?
Yes.
Okay. If you misread it, don't worry about that. It's not a big deal. So we know that's 12, right?
Yes.
Now, how do we get, Evan, here, redeem yourself. How do we get K1?
Find it at t equals 0.
Okay, what do I write?
You just plug in 0 for t, which sets e to 1.
Right.
So it's VC 0.
What's this?
So that equal to 0?
9, right?
Oh, yep. Okay.
I'm so glad you're doing this. This is perfect. Not quite awake or whatever. You are the perfect person to answer because you're doing all the things that everybody else will do in the quiz. I'm so glad I talked to you. All right. So this is 9, right? You'll notice 9 is not 0. And what is K1 then?
-3.
-3. Yeah.
-3. Agreed, class? Now, don't worry. You're going to stumble and stuff like this, but you're going to learn to be very attentive doing these problems. Detail is everything in engineering. It's the difference between profit and bust, between a thing working and or blowing up. And you Emmys probably know this from experience by now. Or I don't know what the A's do. And I'm sorry, I wish I could say something more profound about the industrial people and fiber and polymer, but my experience is limited. So now I can say that VC of t is equal to what? -3, right? Oh, let's go back here and make sure. Here I got K1 is -3, right? So now it's -3 times e to the minus t over tau. I know tau is 0.9 plus 12. Isn't that right?
Yeah.
You agree?
Mhm.
Yeah.
I'm looking for some affirmation. All right. I'm so glad you affirmed that. These are RC problems that have initial conditions and final conditions. The trick is always getting the initial voltage, the final voltage, and R Thevenin correctly, and then assembling the equation. Now, I'm going to say this over and over again. Always find the voltage across a capacitor no matter what the problem asks. I'm going to show you where I got that problem, and then I'm going to show you something. This is out of the old Irwin book that I've taken problems from before. Now, you all see here, this is the problem I talked about, right? Here's what's typically asked. They'll say, well, I want to know the current through this 3K. You don't think about that current. You get this voltage. You with me? Now listen carefully. If they want the current through this 3K, that current right there, just listen. Well, once I get this voltage right here, you might as well ground this. Don't you see the current here through that 3K would be this voltage, because that's the positive terminal, right? Would be VC of t minus 12 divided by 3K. How many see that? Right? I'm looking at the voltage difference across that resistor divided by the value of the resistor to get that current. That's used all the time. I will ask on a quiz, I want the current through the 3K here. And what people will do is say, well, of course, it's going to be 2 milliamps. Yeah, it actually is in this case, because once that switch opens, it is 2 milliamps for t greater than 0. But I'll ask you things about resistive currents. I'll ask you things that you would know. If you do all the problems, you'll be very quick, and you say, oh, this is how you do it. I see that, I see that. But if you haven't and you're confused, you'll be totally lost. And that's the way the quizzes and the tests are structured in this class. If you know what you're doing, you're going to really do well. And if you don't, you probably don't know what to even ask. So try to understand what I'm trying to do to you is encourage you to work on this stuff steadily. Between every lecture, do the homework, and if you have questions or you don't understand something, please ask me. Now, I'm going to give you some more problems. I'm basically done with my office hour extension of the class, thank God. But now I will answer any questions regarding this. And the quiz solutions are up there. I'm just going to make a comment, and I don't know if my grader's on or not. But in my opinion, I might be wrong about this, and he'll correct me. The biggest single concern and problem was not the theory behind the problems. It was using your calculators. People messed up everything. Don't do that again. When I say you must know how to use your calculators, there's no forgiveness. There is no forgiveness. You can't argue with me. You can't beg with me. You can't call the dean. You have to know how to use the instruments that you make your living at. And the calculator is one of them, as well as the computer. Now, in fairness, if this was a much more difficult problem where I had like 4 or 5 differential equations, then I cut people slack because I wouldn't be asking for the final answer. I'd be asking for the form of the answer in terms of an equation. But I just want you to know this. I'm not trying to be unfair, but you've got to hone your skill with your calculator and your computer, because in the real world, it's murder out there if you are clumsy and really, in my opinion, if you're not attentive to detail. Now, the quiz solutions are up there, and I'm just going to mention these for a second. The first problem was to find V naught. First, can everybody see this?
Yeah.
To find V naught, it is a very simple voltage division problem. You basically have 2 impedances that are in series. The 2 plus J10 is one impedance. The minus J12 is another. You have a source that's complex. 10 at 30 degrees is the source. To get this, and this is the only thing I wanted to do, to check to make sure you knew how to use your calculator. To get this voltage here, I simply take this voltage, which is the source voltage, multiply it by the voltage division equation, which is minus 12 over 2 plus J10 minus 12, which is really 2 minus J2, and that's this. And that will give you this, right? You can go ahead and make sure your calculators can do this seamlessly and quickly. It should be an almost a given, just as if these things were real valued, not imaginary. Now, the second equation, or the second problem, was this. And here, the only thing I asked for was the actual V naught across here. So, and by the way, this was an open problem, but I said use nodal analysis. People checked it, I'm sure, with Thevin. Thevin will work for this one perfectly. Anything works with. So for this, to use nodal, you say that the current going in, which is 2 at 60 degrees, that's going into this node. There's only one node in this one, right? Just V naught goes from here to ground. That one's known. You put in a ground, and you say 2 at 60 degrees, right? That's the side, is equal to V naught over 30, right there, plus V naught over J10 right there, plus, and then I3 is V naught minus J10 30, that's this, divided by 10, and you solve it. Now, how you solve it doesn't matter on your calculator. When you have this equation, the final value of V naught should be automatic. It should be nearly impossible to mess that up, but the problem will always be that you're clumsy with your calculators, in my opinion. Don't be. Learn how to do it quickly and efficiently. I did not on purpose giving you a 2x2 matrix. They take a little more time, and when you're just getting used to all sorts of complex notation, they can be a bit more problematic. But the next quiz that will have this, or test that has this, will have 2x2 matrices. And you have to know how to do this. Is everybody clear on that? They're hanging around? I'm trying to make absolutely clear that you will be expected to do that. 2x2 matrices with complex numbers, and the complex numbers can be given like this, magnitude and angle, or like 2 plus J5, something like that. And I'm trying to be as crystal clear about this as I can. Don't assume you can get away with not knowing something related to this. Now, when it comes to the transient problems, tonight's work will be all RC circuits. I've got a whole bunch of them. As a matter of fact, if I can, let me do one thing. Give me 1 second. You understand what I'm trying to talk about this right now. Give me 1 second. I'm trying to get this. Yeah. So what I wanted to do is show you some of the things you can get. Now, these are standard type of problems where they have a switch and it's no longer just a switch that opens and closes and that has no second state. You see how a switch is closed here. This voltage is in for t less than 0. So really, to get the voltage across this capacitor, you use voltage division between R2 and R1 for t less than 0, because the capacitor would be an open circuit. And that's what they show here. You all see this, class? All right. All right, now, that voltage would be what? 12 times 3 over 9, right? Or 12 times 1/3, it would be 4 volts for t less than 0. You all see that? I know there's only a few of you left, but you with me? This is the voltage across this capacitor for t less than 0. Remember, the switch was closed here at t equals 0. It transitions from state 1 to 2. Can you see it?
Yeah.
That means this circuit is equivalent to this circuit for t less than 0 to calculate this voltage. He removes the capacitance and he gets this voltage by simple voltage division, which would be 3 over 3 plus 6, or 1/3 times 12, right? Or 4 volts. Now, when it's in the second state here, look, when it's in the second state, this is important, I didn't get to this today. You see how there's no voltage or current sources in this circuit? Y'all see that? The minute you see no voltage or current sources in the circuit, the final state is 0 energy. It means the voltage on the capacitor would go to 0. With me? So you know the voltage go to 0. Now the next thing you have to do is get R Thevenin across that capacitor. You all see that R Thevenin across there will just be R1 in parallel with R2? Can you see that? Remember, remove the capacitor, find the equivalent resistance. It would be R1 in parallel with R2. It doesn't matter what they are. In this case, it's 6K and 3K. So it would be in parallel would be 2K, right? 6 times 3 is 18 over 9 would be 2K. Correct, class?
Yeah.
All right. That's the typical kind of problem. And you just get a little more complicated. Oh, that's an inductor. Like this one, what changes as far as the complexity? I may give you these. Take a look at this. They want the voltage across the capacitor for what? T greater than 0. Now take a look. What happens? What's different? For t less than 0, that's closed, right?
Yeah.
All right. For t less than 0, it's closed. Rip that capacitor out for a second. I'm looking for the voltage across these two dangling leads, which is the voltage across the 4 and 2K in series. Do you agree?
Yeah.
Now, here's the thing. People that cramp, they'll go for this voltage, V out of T. Complete waste of time. You get that at the end. You hear me? Are you with me? You don't get this voltage. You get this voltage. You will get this voltage. But now we've got the actual value of the voltage right here for T less than 0 by taking what? I take 4 and 2 is 6K divided by 4 and 2, 6 plus 3 is 9. So I take what? 6/9, right? Or 2/3 times 12. Agreed, class?
Mhm.
And that's 8 volts, isn't it?
Yes.
It's okay, I think too, but I better watch what I say. I look like an idiot. All right, so I've got 8 volts. Now, what's the final state? Just look at this. When this opens up, is there a source here?
No.
No.
Y'all see it's no. So that means the voltage across the capacitor goes to zip. Agreed?
Yeah.
Good. Now, what's R Thevenin? Remember, R Thevenin is for T greater than 0. So this part of the circuit right here is removed, isn't it? When that switch flips? What would R Thevenin be?
Would it be just 4 plus 3?
2, isn't that 2?
Yeah,
Is
I
it?
can
Yeah.
agree.
I'm sorry if it's too small. 2K, right? So it'd be 6K, right?
Yes.
And tau would be 100 microfarads times 6K, right? Just leave it at that for now. You agree?
Yes.
Then you set up the equation, lo and behold, that's what you get for VC of T. All right, Jessica, time for one more question for you. Ready? What would the current be through the 2K for T greater than 0?
would it just be 100 divided by 2? No.
Think about now, isn't that current the same current through the 4K?
Yes, so
And just listen, don't we have a voltage across the 4 plus 2K? We've got VC of T, right?
yeah.
So wouldn't it just be VC of T by 6K? Wouldn't that be the current through that 2K?
Yes. So it'd be 100 divided by 4 plus 2.
Then not 100, but it would be VC of T
Okay.
divided by 6K.
Yes, VC.
But you understand how kids can get so confused if I ask that and they haven't thought about it. They haven't worked through it. Oh, you've never asked that, Doctor. I'm asking it now. I'm just telling you, these are typical common questions. And there'll be questions like this on the fundamentals of engineering exam. Now, I'm going to give you a bunch of problems. I almost feel like just giving the ones with the answers here, not the actual way to work it. But like this problem is great because it's got an initial or final condition of 12 volts and it's got an initial condition that would be 12 minus 5 or 7 volts. And we can prove that. But these are the kind you got to struggle with to get the answer. Are you okay with that?
Yes.
All right, now overall, did you understand this lecture? I only got 3 of you left.
Yeah.
All right. I'm trying to communicate clearly about the expectations and about the type of problems. I'm going to give you a bunch of problems. Please do them, okay?
Okay.
And unfortunately, nobody's around right now, but if you have very specific questions about a specific calculator, then I'm going to ask you to please go to your GroupMe page, and I'm staying off of it. Try to find somebody to help you. If you can't, ring me, and I'll try to get somebody. Is everybody here good with your calculators?
Yes.
Okay. Now, I'll tell you, if you, for whatever reason, fumbled your calculators this time, be thankful for it because you're going to be very wary and you'll know it. The big deal is, and I didn't say this to the class, but I will. One of those quizzes is going to get punted. So your low quiz will get punted from your average. I expect everybody to have one quiz removed from the average quiz grade. But I want you to know this. This is not a course that you can slack off and expect to get through. It's like thermo or something like that. It requires being attentive, but it's not complicated. Any engineer that's worth his salt should be able to get an A in this course with the appropriate amount of effort, 2 to 3 hours between each lecture. That's the way I don't teach this at a high level, and I don't make you know Laplace transforms like Gross does and stuff. Okay, and I don't even know what the other class, they're so far ahead of us, but my opinion is a lot of kids don't understand the fundamentals, and then they're doing power and all that other stuff, 3-phase power, and they're really lost. Does anybody know anybody in the other classes?
I took a similar class to this, like I dropped it when everything went to crap with the pandemic. But right about this time in the spring, we were going over op amps. And first we did op amps, then we did AC applied to op amps.
Wait, is this in this course?
Yeah, Intro to Electrical Engineering.
They did this in this course without going through transients?
They went through transients. They went through it very quickly.
I know. And that's a mistake. And I've taught this course too many times. You cannot assume everybody sees what is obvious to them, okay? Especially when they do power, 3-phase power. Operational amplifiers are very easy if it's taught right. They're very complicated if it's not. Okay, Brantley, did you have any questions?
Yeah, I had a question about quiz 3.
Go ahead.
So I didn't use voltage division. I tried to do it a different way, and
all right, any way you want to do it's fine.
Yeah, well, I did it wrong.
Oh, well then, you got to know. Let me restate. If you know what you're doing, you can use any method. It's not required. You could calculate the current first and then multiply the current by the actual impedance. That's fine too.
That's exactly what I tried to do, and I just want to see where I messed up.
What kind of calculator?
Oh, I'm fine on the calculator. The calculator stuff I actually understand.
Okay, let's do it, Brantley.
I've been doing fine in the homework with it.
You're good with that right here? Second or first problem?
The first problem.
Oh, first.
That's why I was so confused, because I thought I was prepared for
Brantley, just listen to me and tell me where the problem is.
Okay.
All right, do you agree that there's 10 at 30 degrees is the voltage source?
Yes.
And do you agree that the series resistance that would limit current would be 2 plus J10 minus J2, 12, right?
Yes, I see that through voltage division, but what I tried
No,
to
it
do,
isn't voltage division. It's just you sum the impedances and dividing into the actual, hold on for 1 second. Let me do this for you. Let me do this. I'm going to call that current I. Right? Just I of T. Now watch, or I of T. Just I, capital I. Now I'm going to say over here, right here, I'm going to say I is equal to, is going to be 10 at 30 degrees, right? Give me 1 second. Then I'm going to take that and divide it by the sum of 2, right? Plus J10, right? Or plus 10J, however you want to write it. And then I'm going to take that, and then it's minus J12, right?
okay.
Right? All right, now let me do this. All right, that is supposed to be a 1 there. And that's going to give a value. And I can calculate that value, but you agree with that, right? Once you have that value, that current flows through each element, right? Now, if you look at that, isn't this right here, the bottom part, 2 plus J10 minus J12, isn't that just 2 minus J2?
Yes.
All right, now, if that's 2 minus J2, and you got 10 at 30 up top, to get the voltage right here, I just have to multiply it by minus 12. Do you agree?
Okay.
Right? All right, well, that's exactly what's right here.
Okay.
Minus 12. And if you know how to do your calculators, that's going to be the real and imaginary, and this will be the magnitude and angle.
Okay.
And so what kind of calculator?
TI-84.
See, unfortunately, because I don't use TI products, I had a TI a long time ago, and I have everything I've had. I mean, I have Hewlett Packard, and I think they're I don't even think they make them anymore, but it's reverse Polish notation. So it's like a stack on if you don't know what a microcontroller or microprocessor is, you put in the things in the opposite order you're going to use them. The last thing in is the first thing you're going to use. And so it's different on TI. You're literally putting 2 and then the time signal 2 and then equal 4. And my calculator, I enter 2, and then I'd say times, and it comes out. So it's the variables first, then the operation. Does anybody know what I'm talking about here? I only got 3 people on.
You lost me.
Well, that's if you're in electrical engineering. This is when you do stack programming and microcontrollers, and it's basically assembly language. And I guess you don't get assembly in some of your other courses.
I've heard about assembly. Like it's apparently it's supposed to be a simpler or more intuitive way to code that they could teach like line workers or people who didn't have a traditional engineering education to program.
And I'm going to level with you too. Assembly is a very low level language. So an assembly program, you don't have to, basically when you compile it and stuff, it's trivial. It's so fast. All right, a higher order like Python or MATLAB, then to compile that into a C, and then it takes some time, and it can really get bogged down. All right. Now, again, your calculators are your friends and your enemies. If you got to know how to use them with the equations, you're right. And I would recommend using Octave or MATLAB to check and make sure. If you punch numbers in, you get the same thing both places, your calculator or or on Octave. Now, Octave, I showed you a little bit, but it's the same thing as MATLAB. I don't use MATLAB unless I have to, because I have to get this FlexLM license. I don't own a copy. Okay, are we good? Now, again, people are going to be furious that they've made trivial mistakes in their mind and they got a bad grade. That's okay. I'd rather you be furious now than come test time and be calm and relaxed until the test, then you really blow it.
When is that test going to be?
We're going to...
If you have any idea.
Yeah, I'll tell you. I think right before Thanksgiving. And the reason is this. Because if you have too much material on the final that you have not... See, when you go for an in-class test, for starters, it's easier. It's much easier, in my opinion. That's just me. But I look at the Zoom quiz that I gave you versus the in-class quizzes and the scores and everything like that. It was much, I say, easier. I'd say there's less complicated steps involved. All right, now, having said that, on the Zoom final, if in fact I think they're still going to break, but anymore with Auburn, I'm not sure what they're going to do because of football. Because we have, I'm not even sure where the Iron Bowls played this year. But when it comes to football, they want their kids around. The merchants want them around. That might be a wrong motive. And hopefully everybody's going to be over COVID by then, or at least it'll be minimal. But if they are going to go home and get the file, then you're getting a Zoom file, and that can be a headache. That's my opinion. Just my opinion. On the last quiz, we had 10s and 10s, and we had 0s and 0s. And I can only tell you that a lot of people they got a 0 because they didn't show up. I have an excuse, and that's unfortunate.
So, this is going to seem like a simple question, but I missed a little bit of class last week. My dog died last Monday, and it kind of threw me off.
I'm very sorry to hear that.
Yeah, I found out like the worst way too. He had a bladder infection for like a month. My mom called me, said he's got bad news. They did an ultrasound, and he had late stage prostate cancer, and they put him down, a few hours before they told me. So, I was out of it for most of last week.
I am sorry. I'm sorry to hear that.
Could you go over the basics of like how do you treat inductors and how do you treat capacitors? Like I know they're very similar to resistors, and how do you add them up?
Oh, you want to add them up?
Or like how do you combine them? I got the feeling that inductors you add like a series.
That's right, but I didn't even cover that. If you're looking at a book doing this, don't worry about that. We haven't even covered it. The only thing I ask you to do is get the equivalent. Find if you've got an inductor of 3 Henries and omega is say 10 radians per second, then the inductive impedance would be 3 times 10 or 30, but you put a J in front of it, it would be J30. And if it was a capacitor, it would be 1 over J omega C. It's really, I don't mean to make it trivial, but I'll just show you. If somebody else wants to hop in and make it easy, it's literally this easy. If you have an inductor like so, L, this is for steady state operation. It has a complex impedance. And we're at a constant frequency of omega. Do you know how to find omega?
No.
Well, if you have cosine of omega t plus a phase angle, it's the coefficient of t. If you have any kind of a V naught here, this will be constant for any kind of AC circuit. So the impedance of an inductor would be equal to J omega L. Now, usually, at least for the quiz, I gave you the product of omega times L.
All right.
Then for a capacitor, the impedance of this is going to be 1 over J omega C, or it's just minus J over omega C. And the units are ohms. And then you treat that just as you would a resistor.
All right. Okay. So, all right, yes, that makes sense. I was just trying to put that in context of what we were talking about today, as far as once you have t equals infinity.
No, this doesn't have anything to, this
Oh,
is,
no,
yeah.
I'm just trying to contextualize this information in terms of the lecture we had today.
Yeah, this is transients, has nothing to do with this.
Okay. All
If you
right.
get a chance, look at some of the lecture notes and you'll see, okay? Or look at the video. Jessica, are you putting this on YouTube or where are you putting it?
I was only able to record one of them, which was from the class of the 14th, because the other day, the first time I was a co-host, for some reason it didn't record. I think when I become a co-host, I have to click record, just like today. Today I have to click again record for it to go to my computer.
Yeah, you do. You're right. All
I
right.
also have a recording of this.
Yeah, both of you are recording, which is good. Put up both links.
Yes. I shared a link on one of the groupies.
Can you put something like RC transients to label that so they know?
Okay.
Because these
All right.
kids will,